Hello everyone, this is Jerome, and this video will be about the end of the year project and what we've learned in the past year in chemistry. And the past year in chemistry has introduced us to new topics that we were surprised about and learned a lot about. And due to this, we have a better understanding of our world. And from the past year, we've concluded that the most impactful topics were stoichiometry, gas laws, and solutions. And this presentation will include reaction demonstrations, explanations, and examples. So let's get started. Starting off with the first topic, we have solutions. So solutions are homogeneous mixtures, and these are mixtures consisting of solvent, which is a substance dissolving the solute, which is usually water, and a solute, the substance being dissolved. And usually uh, highly electronegative substances like polar covalent compounds and ionic compounds are the solutes. So basically, the polar water molecules dissolve the molecule by ripping apart the bonds, allowing them to mix in a uniform manner. And the ability for the substance to dissolve depends on a few factors, and these factors are the solvent's temperature, the solvent's volume, and the solute's chemical identity. So first off, we have solubility. So solubility is a solute's potential ability to dissolve in a solvent, and each substance has a unique solubility given certain parameters. And we basically have this solubility graph where the y-axis is solubility per 100 grams and the x-axis is theoretical temperature. And this is a graph where the volume is constant. So uh, it is demonstrated how a parameter, in this case it's the temperature, can affect the solubility of a substance. And the general trend is that the solubility increases when the temperature increases. And we have exceptions like cerium sulfate, which doesn't follow this trend. And next we have the solubility chart. So we have this because not every compound is soluble in water, and we have a few solubility rules, and so these solubility rules are elements whose ionic compounds are always soluble, and we have the elements in the solubility chart which we can use. And now moving on to molarity. So molarity basically describes the concentration of a solute in a given solution. And the equation for this is uh, m equals n over v, where m is the molarity, n is the moles of solute, and v is the volume of the solvent in liters. And n and v are proportionate to molarity, and as so basically when moles are constant, increasing the volume decreases the molarity, as there are less parts of solute per unit volume and vice versa. And the same is true when volume is constant. And now moving on to saturation. Saturation basically describes the reaching of the limit of how much the solvent can hold a given solute. And for example, if there's a limit of the amount of NaCl that can be dissolved in 10 ml of water, there can be three main states. You have unsaturated, saturated, and supersaturated. Unsaturated is when the solvent is not at its limit, and it still has room to dissolve the substance further. Saturated is when the solvent has reached its limit and it cannot dissolve the substance anymore. And supersaturated is when the solvent has gone beyond its limit, and you'll have undissolved particles. And this process can be used where uh, we can lower the solubility of the solvent, forcing molecules to reform and crystallize. And now we have dilution. And dilution is the act of reducing the uh, concentration of a solution. So usually this happens by increasing the solvent's volume. And uh, the equation for this is M1V1 equals M2V2, where M1 is the initial molarity, V1 is the initial volume, V2 is the volume after the dilution, and M2 is the molarity after the dilution or concentration. And this equation shows us that molarity and volume are inversely proportional. So finally, we'll have the demonstration for the solutions part. So in this, we'll be regrowing the citric acid crystals from the failed examples. So we'll be taking some of the failed citric acid crystals and adding them to a Pyrex container. And we'll be adding boiling water so that there's a saturated solution being created. And and a solution needs to be supersaturated for the crystals to grow. So we'll be leaving the supersaturated solution outside for the water to evaporate. And as the volume of the solvent decreases, there's less place for the solute for it to dissolve, and the undissolved solids bond in a lattice pattern, causing the flat surfaces and sharp edges, which is what we see as the crystals. And we'll be looking at the crystals now.
And this is the result from crystallization. Um, yeah, it's not as perfect as I wanted it to be, but yeah, nothing is. So yeah, more. That's the solutions part.
So now moving on to our next topic, gas laws. So basic introduction to gas laws. So these are laws that explain the behavior of gases in relation to pressure, volume, temperature, and the amount of gas. And a key theory is the kinetic molecular theory. And in this, we can say that the gas particles are in constant random rapid motion, and also that there's no gain or loss in the energy during collisions, or that the collisions are elastic, and and also that the molecules colliding with the walls causes gas pressure. And another important concept in relation to gas laws are standard temperature and pressure units. And for temperature, we have 273.15 Kelvin, or 0 degrees Celsius, and we used Kelvin for our units, our standard unit. And for pressure, we have atmospheres, and for the standard pressure, it is 1 atm. And another conversion factor we'll be using later is 1 mole of gas at STP is equal to 22.4 liters of gas. And now going to our first gas law, we have the Boyle's law, and this law shows a relationship between pressure and volume, and that they are inversely proportional. As the pressure increases, the volume decreases, and as the pressure decreases, the volume increases. And we have a simple practice problem, and this says that if there's gas at 25 degrees Celsius, it occupies 3.6 liters at a given pressure of 1 atm. What will be the volume if the pressure is increased to 2.5 atmospheres? So we can just use the formula and plug in the values. So P1 would be 1 atm, and V1 would be 3.6 liters. And we're solving for V2, which is the volume at 2.5 atm, and we can find the answers, which is 1.44 liters. And now moving on to the next two laws, we have Charles's law and Gay-Lussac's law. So the Charles's law shows the relationship between volume and temperature, and they're directly proportional. So V1 over T1 equals V2 over T2. And we can see a simple practice problem. So one key thing to note is when they give it in Celsius, the values in Celsius, we need to convert it to Kelvin, and then we can plug in the values. And then we have the Gay-Lussac's law, which involves the relationship between pressure and temperature. So, and just like the Charles's law, they're directly proportional. So P1 over T1 equals P2 over T2. And we have a similar practice problem, and we can convert the temperature from Celsius to Kelvin, and then we can plug in the values. And now we have the Avogadro's law, and this is the relationship between volume and the amount of gas, and they're also directly proportional. So the formula is V1 over N1 equals V2 over N2. And we have a simple practice problem. So a sample of gas originally occupies 0.5 liters with 2.5 moles present. And if the volume is increased to 0.75 liters, what would be the moles? So basically 0.5 liters would be the initial volume, V1, 2.5 moles would be N1, and 0.75 liters would be V2. And we're solving for N2. And next we have the combined gas law. So this is basically all of the gas laws put together in one formula. And we can use this when there are multiple variables, and we can also eliminate any of the variables if it is constant. And a simple practice problem we have is, what is the volume of gas at 2 atmospheres and 200 Kelvin if its original volume was 300 liters at 0.25 atmospheres and 400 Kelvin? So as we can see, in this particular problem, the amount of moles is constant, so we don't have to use the variable, and we can just use P1 V1 over T1 equals P2 V2 over T2 to plug in and solve this problem. Then finally we have the ideal gas law with the formula of PV equals nRT, and R is the ideal gas constant of 0.0821 liters atm divided by mole Kelvin. And so basically, if we isolate R, we can get PV over NT. So PV over NT is always equal to this constant. And another simple practice problem is, if a container has 3 moles of gas with a volume of 60 liters at a temperature of 400 Kelvin, what is the pressure in the container? So as we can see, we have the variables for volume, temperature, and the number of moles, and we need to find out pressure. And R is 0.0821, and we can plug it in by isolating the pressure, and we get 1.64 atmospheres. And next we have the Graham's law of effusion, which allows us to find out the rate of effusion. And effusion is when a gas escapes through a tiny hole in a container. And the general rule for the rate of effusion is gases with lower molar masses effuse faster than ones with higher molar masses. And For the formula, the rate of effusion is inversely proportional uh, to the square root of its molar masses. So basically, the rate of molar mass, the rate of A or rate of B equals the square root of the molar mass B over molar mass A. So that's why it's inversely proportional. And a simple practice problem is how much faster does hydrogen effuse through a tiny hole than argon. So we can set rate A as hydrogen and rate B as argon, and we can solve by doing the square root of 39.95 divided by 1.01. So 39.95 is the molar mass of argon, and the molar mass of hydrogen is 1.01, and we get 6.29. So this basically shows us that a hydrogen effuses 6.29 times faster than argon. So this is basically because hydrogen has a lower molar mass, so it basically effuses faster. And then we also have the partial pressure using Dalton's law. So this is a pretty simple concept. So to find the total pressure, we add all of the partial pressures of each gas in a mixture, and this basically gives us the total pressure. And the final experiment was the boiling water with ice experiment. So this is a pretty simple experiment. We can use a flask and we can boil water. And once the water is boiled, we can close the container and we can invert it, and we can add some ice on top of it. And if we check after a couple of seconds, we can see that the water inside starts to boil. And so this basically happens because the pressure inside the flask is lowered because the ice condenses the water vapor inside the container, and when it condenses it, it has more space and the water starts to boil as it requires less heat to boil.
This is a quick demonstration of how ice can boil water. So we got some ice over here, and you can see the water is boiling. There are pockets of water vapor forming at the bottom to soon rise up, and yeah, that's how you boil water with ice.